Welcome back. Today we're going to talk about derivative of logarithmic function. Section 6.4. I'm going to do this in two parts. This is part one of the lecture video. I'm going to only focus on the ln function. We're going to talk about the derivative of an integral of ln x. And the general logarithmic and exponential function, we'll discuss the derivative of that in the next video. Okay, so first, let's say, given the function ln x, let's say f of x equal to ln x is given, can we figure out what is the derivative? What we know at the moment is that if y equal to ln x, then there is a corresponding exponential form that corresponds to this. We can say x must equal e to the power y. This is the inverse function. This is how we introduce the the logarithmic function, by discussing it as an inverse of the exponential. So now we can take the derivative of this function, this equation. We can take the derivative. Therefore, we can create a relation between these two through the derivative, and we hopefully can find the derivative of the ln x function later. So let's first find out what is the derivative of this equation. I'll say x equals e to the y, and we take the derivative of that. What would be the derivative? Derivative of x. What do we take the derivative with respect to? Is we take the derivative with respect to x. So I should write it this way. Therefore, the derivative of x would be simply 1. Derivative of e to the power y. Derivative of e to the y is e to the y multiplied by derivative of the exponent, which is dy over dx, or y prime. Okay, so if we're solving for dy over dx, then I can say dy over dx simply 1 divided by e to the power y. Right? So therefore, if this is the equation y equal to ln x, then I found out that the derivative is 1 divided by e to the power y. But what is e to the power y? E to the power y is simply x. So I can say this could be simplified to 1 over x. So what does this tell us? It tells us that the derivative of y with respect to x is simply 1 over x. And what was y? Y was ln x, which means we found the derivative of the function f equal ln x. So I can answer this and say f prime x would be simply 1 divided by x. And you can generate the ln of u by chain rule. It would be 1 divided by u multiplied by the derivative of the inside function du over dx. In some textbooks they use this format as well. The derivative d over dx, maybe I should write this, d over dx of ln of any function inside, g of x. G is a function. What do we get? One big parentheses. G is an input. You can think about g as u. This is the same as this. U could be a function. So this is simply 1 over g of x multiplied by g of x derivative, or u prime derivative. Sometimes they write it this way, sometimes they write it as g prime of x divided by g of x. It's the same thing. You can use this notation of 1 over u, or you can use the function g or g prime, doesn't really matter. We'll do examples of this, but the main thing is that the derivative of ln x would be simply 1 over x. And this red expression that I wrote here, this is kind of the proof of why the derivative equals 1 over x. This is the proof. Okay, so here, let's answer for some of these. Find the derivatives. What would be derivative of ln x squared? It would be 1 divided by x squared multiplied by d of x squared with respect to dx. There's a chain rule, or you can write it as x squared derivative. Either way is fine. So it would be 1 over x squared times derivative of x squared 2x. You can simplify it. 2x over x squared would be 2 over x. So this would be the derivative. How about d over dx of ln x sine x? Again, this is input. Let me fix this notation. ln of sine. Sine is not multiplied by the ln function. If it was multiplied, we would write it as ln x times sine x. If I write ln of sine x, this is an input. Okay, think about this as like a square root of something like this. Operates, ln operates on the sine function. So it's a composition of functions. So what would be the derivative? The derivative would be 1 divided by the input function. This is the inside function. So sine x. You can think about it again as u if you want. Multiply by u prime. So multiply by sine x derivative. What is sine x derivative? It is cosine x. Derivative of sine is cosine. And this could be written as cosine x divided by sine x, which is the same as cotangent x. So the derivative of ln sine x turns out to be cotangent. And here, what if it was the other way? What if it was derivative of sine ln x? In this case, this is the input function. Say, okay, what is the derivative of sine of u? It would be derivative of the outside function. Derivative of sine is cosine. Cosine of u, so cosine of ln x. Multiply by the ln x derivative. ln x derivative. This is chain rule. So cosine of ln x multiply by the derivative of ln x, simply 1 over x. You can write it as cosine ln x divided by, and one important thing, do not cancel out these two. This is not possible. Don't do that. That's it. This is a simplified form of the result. Okay, just to make sure that you guys do not mix it with the product. Let me show you a product here. If we have d over dx of, let's say, ln x sine x, this would be, you should apply a product rule. It would be derivative of the first function multiplied by the second plus the first function times the derivative of the second one. And then you can calculate the derivative of ln x is 1 over x times sine x plus ln x times the derivative of sine x is cosine. This is the difference between product of ln x and sine x and ln composed with the sine function. Okay. How about ln x? Again, this is an input to the ln function. So what you can think about is this is u, this ln x inside. So the derivative would be 1 divided by u, which is 1 divided by ln x, multiply by the derivative of the inside function, ln x derivative. Again, this is 1 over u times u prime, chain rule. And this would be d over dx of ln u. If we are looking for the derivative of something like this, I should write d over dx. So this is 1 over u, which is 1 divided by ln x, and d over dx is just the derivative of the inside. And that is simply 1 over ln x times the derivative of ln x is 1 over x. You can write this as 1 over x ln x. Do not multiply this x with that 1 inside. This. Okay. Okay, so taking the derivative is not too complicated as long as you use the chain rule properly. Here, one more example. All the stuff that we have learned for the derivative, you can apply again here. You can do product rule, quotient rule, chain rule, everything. Finding local maximum, inflection point, everything is applying as well to these functions. So here's an example of it. Find the increasing and decreasing interval for this function, x squared ln x. One thing that is important is that you notice every time you give an ln function, you should always check for the domain. It's like you have the square root of x. It's important that the input must be always positive. The difference between square root and ln is that square root, you can put 0 inside ln function. 0 is not allowed either. So the domain of this function is 0 to infinity. If you're looking for increasing and decreasing intervals, you're not allowed to go to the negative number. This is important to find the domain before you calculate the increasing and then decreasing interval. So if you want to find the increasing and decreasing interval, find out what is f prime x. Find the critical numbers. So what would be the f prime? This is the product of two functions. So you say x squared derivative times ln x plus x squared times ln x derivative. And what we get is 2x times ln x plus x squared times derivative of ln 1 over x. And that is 2x ln x. X squared and 1 over x, you can simplify it to simply x. You can factor out an x as well. X times 2 ln x plus 1. So this would be the simplified version of the derivative. We need to find out where is the critical number. So we said either we say the derivative does not exist or the derivative is equal to 0. Since we picked the domain to be 0 to infinity, this function has well-defined derivative everywhere. So we just need to figure out where is the derivative equal to 0. So I'll say x times 2 ln x plus 1 equal to 0. This is fine to find critical numbers. From chapter 3, I think. So what we can say is either x equals to 0, either this is 0, or the parentheses is 0, or 2 ln x plus 1 equals to 0. One important thing, x cannot be 0 since it's not in the domain. This is not allowed. How about the other one? 2 ln x plus 1 equal to 0. That means ln x equals negative 1/2. If you move subtract the 1 and divide by 2. So what is x? If you're looking for x, you can always write an exponential. What is the corresponding exponential? If you have x equals ln y, y equal ln x, remember the corresponding exponential would be x equals e to the y. Or if you forget this, relation, you don't remember this, you always raise both sides to the inverse function. What is the inverse of ln? It's the exponential. So I write e to that power, e to this power. E to the power ln x is simply x. This is the composition of x and the composition of exponential and log. And on the right side, I have e to the negative 1/2. So I found out what is x. X is e to the negative 1/2. It may look complicated, but e to the negative 1/2 is, let me simplify it. E to the negative 1/2 is the same as e to the positive 1/2 in the denominator, 1 divided by that. And what is e to the power 1/2? It's 1 divided by square root of e. So we found the x value for the critical number. It's 1 divided by square root of e. So if I draw the number line, I should specify that the domain is from 0, so I cannot go beyond 0. And 1 divided by square root of e, somewhere here, the positive number. So what do we need to do? Pick test points to find the increasing and decreasing interval. I'll pick something less than 1 over square root of e. You can pick this as a decimal number and pick a test point. 1 divided by square root of e is probably close to 1/2 or something like that. So I'm going to pick something very close, small. So I'll pick something like 1 over e squared. You can pick decimal number, use calculator. So at the moment I don't have calculator, so I'll pick this. And on the right side, I'll pick e. It's bigger than 1 divided by square root of e. And if you replace these into the derivative, here's the derivative function. What do we get? highlight this, replacing it here. What we get is 2 times ln of, I should write it. So you'll get 1 divided by e, you can pick e as well. 1 divided by e times 2 ln 1 divided by e plus 1. I replaced x with that to see what do I get as the result for the derivative. This is f prime at 1 divided by e. And what do you get is, you don't need to find out the number, you just need to figure out what is the sign. Again, if you have calculated, it's easy. But what is ln 1 over e? You can write it as e to the power negative 1. 1 divided by e is the same as e to the power negative 1. ln e to the negative 1, this is simply negative 1. That's why I picked 1 over e. So what you have is 2 times negative 1 plus 1, which is negative 1. So what we get at the end is a negative number, negative 1 over e. So it means here I have a negative number. If you replace e, what you get is positive. Everything would be the same, except here you would have e. So you will get f prime of e would be e times 2 ln e plus 1, which would be e times 3. ln e would be simply 1. So you'll get a positive number. So this means function is decreasing here, increasing there. I have a local minimum. It turns out to be an absolute minimum because the function is decreasing then increasing. So this point, this point would be a absolute minimum actually. Okay, so again, everything is still applying to exponential and log functions. The only thing is that you need to be cautious when you take the derivative. When you're applying chain rule, you have to apply them properly. Okay, so here one more important thing that I need to mention, that if the ln is chosen to be ln absolute value of x, the derivative of that is still 1 over x. You may ask, how is that even possible? Let me show you this. If x is positive, then absolute value of x would be exactly x. So the derivative is simply 1 over x. If x is positive, absolute value of x would be still the same as x. But on the other side, if x is negative, what we get is absolute value of a negative number would be a positive number. So it would be negative of whatever that negative number was. And the question is, what is the derivative of ln negative x? It would be 1 divided by negative x multiplied by negative x derivative. What is negative x derivative? Is negative 1. So this negative sign and that negative sign will cancel out and you still get 1 over x. So you can say, okay, the derivative of ln absolute value of x is still 1 over x. The only thing is that important, x cannot be 0 because the derivative would not exist and the function has no value at that point. Okay, and without the absolute value, the domain is restricted to only positive number, but with the absolute value, you can put negative number inside the ln. The absolute value will take care of it. Why do I mention this? I mention it because now if I ask you what is the integral of 1 over x, you can say, okay, x is not restricted to only positive number. It could be negative as well. Therefore, the ln should have an absolute value. If I knew only x is positive, then the result would be the antiderivative of 1 over x is ln x. But since x could be negative, ln of a negative number is not possible. So we require this absolute value. And how do we know this? Is just by going backward in the derivative. If I know the derivative of ln absolute value x, derivative is 1 over x. Therefore, the integral of the right-hand side should be the left-hand side. So the integral of 1 over x must be ln absolute value of x. Plus some constant c, since the constant doesn't really affect anything. Let me write this. Okay. Again, everything will apply to this. You can use substitution methods again for all these stuff. So here first, let's look at the area. They say find the area under this curve. The curve is 1 over x, and if you don't remember how 1 over x looks like, I'll give you an idea. And they say from 1 to e, so 1 over x has a vertical asymptote and a horizontal asymptote here. And on the other side, I don't really care about the left side, but the left side looks like this. Since the domain is picked only from this interval is given from 1 to e, you want to find out what is the area here. That's what we're looking for. And to find that, the area corresponds to the integral. So the area would be the integral from 1 to e of 1 over x dx. And we can integrate now. What is the integral of 1 over x? It would be ln absolute value of x. And you don't need the constancy since there is boundaries from 1 to e. At this moment, if you forget the absolute value, it's totally fine because the inputs are positive. But if it's negative, you should have this absolute value. Just make sure that you always use the absolute value to avoid making mistakes. Okay, replace e in there, you'll get ln absolute value of e. Replace 1 minus ln absolute value of 1. So that is equal to ln e minus ln 1. Ln e is simply 1. ln 1, 0. So the result is 1. So this means this area here is a 1. Okay, so nothing complicated as long as you take the integral correctly. So to make sure that we know how to take the integrals, here are a bunch of more examples. Let's calculate these integrals. Calculate the integral of x divided by x squared plus 1. You might ask yourself, okay, how is this related to integral, to ln? And if you look at this, there is no way to simplify this fraction. So what I can do is I can start by testing substitutions. What if I pick x squared plus 1 to be our substitution? U. Then what do we get the derivative? Write it the other way. U equals to this. So du over dx equals 2x. So therefore du divided by 2x equals dx. So I can write the integral as x divided by u, since we picked x squared plus 1, the denominator. Dx would be du divided by 2x. And here's the good news. The x's can cancel out. What we have is integral 1 divided by u multiplied by du divided by 2. You can write it as 1/2 du. If there is any constant, I recommend writing the constant separately from this term, just to avoid making mistakes. So I can write this as 1/2 integral of 1 over u. If you write this 1 over, this is correct to write as well this way. You can write this 1 over 2u du, but it's kind of hard to guess what is the integral in this case, because the integral is not, this is not the integral. Don't make this mistake. This is not correct. The integral of that is not 1 over 2u. What you should do is write this 1/2 times ln u, sorry, 1/2 times 1 over u. Then now integrate. What is the integral of 1 over u du? We know that one is ln u plus some constancy, sorry, with the absolute value. And this is 1/2 ln u was x squared plus 1 plus some constants. The homework may be picky because you always know that x squared plus 1 is a positive number. So they may say, okay, you don't really need this absolute value. You can simply say this is x squared plus 1 plus c. Since we already know the absolute value, the inside of the absolute value is always positive. If it's not, then you are required to use this absolute value. Okay, how about this one? The integral of tangent x. We don't know the integral of tangent. We know the derivative of it, but not the integral. So how do we take this integral? Let's rewrite it in terms of sine x divided by cosine x. That's the same as tangent. So now I'm going to do the substitution. What do you pick as a substitution? Normally, substitutions, we pick the denominator. for substitutions. I'll pick cosine x. It's not always, but most of the time that's the case. So what do we get for du over dx? It would be sine x to negative sine x. And therefore du divided by negative sine x equals dx. I can rewrite this as sine x divided by, cosine x, we call it u, multiplied by du divided by negative sine x. Again, these two can cancel out. So what we have is integral 1 over u, du divided by negative 1. I can replace that negative and move it outside. So this is negative ln absolute value of u plus some constant c, which is the same as negative ln absolute value of u was cosine x plus some constants. And you notice that we found out what is the integral for tangent x. It's complicated, as not as easy as the derivative. The derivative was secant squared, but the integral wasn't possible. We couldn't possibly calculate the integral without learning the exponential functions. One more. What is the integral of ln x squared divided by x? Here, if you think about this, if I pick x to be the substitution, I haven't done anything. This is an example that not always the denominator is the substitution case. So what do you pick as the substitution? If you pick x squared, let's say you get rid of that x squared. The integral of ln x, we still don't know what that is. If you end up with ln u, as everything simples out. Let's say this simplifies to ln u du. We don't know the integral of that. We know the integral derivative of it, but we don't know the integral of it. So substitution, picking x squared is not a good choice either. How about if we pick the whole thing ln x squared as our substitution? What if I pick u to be ln x squared? And in that case, what would be the derivative? du over dx would be chain rule 1 divided by x squared multiply by the derivative of the inside, which is x squared derivative 2x. So du over dx simplifies to 2 divided by x. You can cancel out one of the x's with here. So I can say du divided by 2 multiplied by x. You can cross multiply this, multiply that, divide here, then you'll end up with x divided by 2 du equals dx. This cross multiply maybe is not a good way to write it. You should multiply x over 2 to both sides. This way you get rid of this x, that 2. And you can multiply dx to both sides. This way this dx will cancel. You'll get dx. Okay. So you can find dx by itself by doing that. Therefore, I can rewrite the integral now. What would be the integral? The numerator, we call the numerator to be u. Denominator is still the x there. What is dx? dx is x du divided by 2. And again, here's the good part of it. The x's will cancel out. And this is, I will always write this outside. It's better to write the constants outside if there is multiplication. So it's 1/2 u du. Now calculate the integral. What is the integral of u? It is u squared over 2. We learned this long time ago, plus some constant c. Just because we're learning about the ln doesn't mean that every integral would be ln. Here, you'll have 1/4 u squared plus c, which is 1/4. Instead of u, we have ln x squared, the whole thing squared plus c. This was our u. I replaced ln x squared for u. Okay, so choosing the right substitution is very important too. Okay, so these are examples for the integral for the simple ln function. Next time we'll talk about what if the base was not e? What if the base was something like 2, 3, square root of 5, whatever. In those cases, what would be the derivative? What would be the integral for both exponential and log functions? So I'm going to stop here, and we'll continue next time. Chapter 6, and 4, part 2.